Hi everyone. It's so nice seeing all these faces again. I hope we have a lot of fun today. So, uh, what's wrong? Uh, how do I get? Oh, okay, okay. Something, something. Nice topic, right? So yeah, yesterday we had a workshop where we just yeah we were looking at monitoring and observability. Today it's more like a story time, but it's really us looking at code. So this topic is a bit of a clickbait. You know, it sounds like we're going to be talking about losing money, but we're actually going to be talking about how to prevent it, right? So there's going to be a bit of code. I mean, just a little bit, and then ask me questions. Let's just all learn together, right? So, so what do you expect to get at the end of this talk? At the end of the talk, you would have maybe learned about a couple data structures. You would have learned about just optimizing very expensive calculations at scale, and you would have learned about the, a concept I'm trying to push for and popularize, which is that we should treat all the requests, all our traffic as data and actually analyze it. But let's just get right into the talk. So in 2018, I worked at this company in Berlin, in Germany, and we had a bit of a legacy problem. So the company was growing very fast. We were acquiring other food delivery brands. Glovo was acquired by Delivery Hero. I think you know Glovo in Kenya, but also brands in Asia. So the systems were mainly built in PHP. Very not that there's anything wrong with PHP, but it was built like a decade ago or before that, and built with different goals in mind. So when we're growing this fast, the systems really could not handle that scale. What does that mean? It meant that on Sundays, usually around noon, we would most likely have an emergency. So things would just go down. Everything would. And then someone would be on fire trying to say, oh, what went down? Was it the database? Was it this? So we figured out that we have to do something about this problem. And part of the solution was to rewrite just some of the hot parts, the really critical bits of the system, and we're going to rewrite it in Go. What can go wrong, right? Rewriting a legacy. How hard can it be? Well, what's the first thing you do when you want to do such a rewrite? You first of all study the legacy code that you want to rewrite. You want to look at it, okay, what are the features? What am I trying to re-implement in my new code? What's going on in there? But the problem with such huge systems is that it's really hard to understand what's going on. And especially in dynamic languages like PHP, you don't really have, in Go we have these concepts of structs, where let's say an endpoint returns a particular struct, you can go look at that struct, see all the fields, and then maybe check how those fields are generated. But in a lot of dynamic languages, you don't have the same luxury. I mean, if you study the code deeply enough, you can, of course, see where everything is defined, but sometimes some subsets of the response is added in completely unrelated parts of the code. So it ends up not being enough to just study that legacy code. So now what do you do when studying the code is not enough? So what we did, I mean, there's a lot of things, and I would like to hear from you. I mean, we'll get to a bit of questions, but I'd like to hear from you how you would approach such a problem. But what we did was that we created a proxy. What's a proxy? So a proxy is a service that sits in front of another service, right? So we wrote this proxy in Go. So we wrote this our new system as a proxy and put it in front of the legacy so that all the traffic that comes in that was going to go to that legacy system would pass through our new system. In the beginning, we didn't do anything in this our proxy. We just sent all of the traffic. But the whole idea was that we could slowly start adding new features on this new proxy. And I'll show you what that proxy code looks like in Go. So this is how you would write such a proxy handler in Go. Go has this HTTP util library that makes it just so simple. I would not even imagine how I would write. I can't imagine how I would write this in a lot of languages, other languages that I use. But there's this new single host reverse proxy method function. So you start up the proxy, you give it the URL that is proxying the request to. In our case, that URL would be a link to the legacy system, right? That legacy system we called Sherlock. I still like that name. And then we make a request to, this is a regular Golang handler. So func, HTTP response writer, etc. So when a request comes in, we start up this recorder that's going to record every single thing, and then use the proxy to handle the request, but via the recorder. Why are we doing that? We're doing that because we want to keep a record of whatever that legacy service was sending, so we can, maybe we can log it to see exactly what's going on, and two, when we implement our version of this, whatever this endpoint is supposed to do, we can compare what the legacy was doing with what our version is returning. And you can see that happening here. So this is our own, like locally we've written some function that would do exactly the same thing that legacy system was doing. And now we get out the response and we compare. So if the implementation was accurate, so first of all, is this big enough? Can you see clearly? It's big enough? So if our local implementation was accurate, then it means that there should be no difference in response between our response body, and what the legacy system was sending. Very bulletproof plan, right? So we're very proud of this. The problem was that in this, and it could have worked quite a lot, but there were some caveats, but let's move on. This was not really the second thing that we do is whenever that error is triggered, where the response from the legacy is not the same as the response from our new logic, we would go to some of these websites, these different websites, to compare what was coming from the old and new, and then figure, okay, we didn't know about this field. We tried to implement it, and that took us very far. But was this enough? Unfortunately not. And if you remember the clickbaity title, we ended up losing like over $2 million worth of orders, right? So it wasn't enough, mainly because for this logic to, first of all, it was very easy to miss some things in the crack. And then second, we were really testing in some markets. So this was a product that was running in 50-something countries. So we're testing in some markets, mainly the Asian market and the Western European market. But it's very hard to very actively test such a migration in everywhere, in every situation, in every combination of rules. It's really hard. And there was no open API documentation. There was nothing like that for this legacy system. So after we had this downtime where we lost all of this, it made us start thinking, what could we really have done better, right? And maybe it's a question I can ask. Does someone want to give their opinion on what they think, how they think this problem could have been solved differently? Does anyone want to take a stab? Want to try?
I think just going by the clickbait title and like what you've explained, um, I think you should have tested in more markets.
I mean, that is correct. So one of the problems with hindsight is that you can only connect the dots looking backwards. You know, when you look backwards, you can say, we should have really just tested. We should have run this particular test and this particular test. And we did test in more market. We just could not really test all combinations of how the system would be used, right? Yeah. Anyone wants to try again? Okay.
Um, I have another interesting suggestion. In a company I worked with in the past, we had this approach called science experiments. So science experiments are things I mean, it's a fancy name, but the whole idea is you run your legacy and your new code path side to side, and you don't actually depend on the result of the new code path, you only depend on the result of the legacy code path, and you create dashboards to show you where the differences are there and if you expect them or not. So basically, before you actually go to production, your new code is running alongside your legacy code side by side. This could be, just calling an internal thing, or it could be an external service call. But in the end, you do a comparison between your legacy code path and your new code path side by side before you actually launch your refactored version.
Thanks. I think that is very insightful, actually. So in this case, we really run this more on staging and then just in a few markets. It's possible that if we kept it in production for some time, we could have caught more of these problems. But yeah, that happened, and then we had to figure out a solution, right? We had to ask ourselves, what could we do better? How could we have prevented this issue? But it also became clear that this was a common problem, that like projects maybe developers would make some small changes that maybe are incompatible with how some clients are using their products, and then their system just breaks and things go wrong. So we had to ask this question, like, could we analyze this traffic, the traffic that we're handling in production, and use that data to, for example, generate an open API specification, deeply understand how a system is supposed to work, and then maybe even have some kind of validations to catch any new changes, breaking changes, or errors, or just behavior just any new behavior. And we actually got this idea because we're scaling very fast, right? And we wanted to know what our systems can handle. So we set up this load testing workflow where every week we would run these load tests across the company. So we wanted to make sure that our systems can always handle 3 times the last production peak. But when we did the load tests, just using the naive low cost or K6 and the rest, we found out very quickly that most of the traffic would just be handled by cache, or even just the database. The databases, if you use Postgres has this hot data concept where data that you fetch very frequently, it keeps it in a special place. So when you do load tests, you think, oh, my system can handle 100,000 requests per minute. But then it's just because you are basically hitting the same data constantly, and your load tests are basically wrong. And anyone who has written a benchmark, even just a code benchmark, has probably experienced similar problems as well. So what was the solution? We found out that if we recorded production traffic, we could actually replay the real production traffic, maybe change it a bit so that there's no we're not actually causing issues for customers. But if we take real production traffic, multiplied by 3, and then throw it at these servers, then we're no longer just requesting the same data in the name of load test, but we're actually really testing and seeing that can our system handle the real production traffic but times 3. So we did this for some time and it worked for load tests. So we figured, okay, using production traffic for load test was working. How about we use it for other things, right? For example, oh yeah, so that's for load tests. So this worked very well for load testing. So how about we use it for catching breaking changes and maybe generating an open API schema to understand our systems? And what did we do? So here's an example. I just want to walk you through the mental model. So you have a request, or you have an endpoint, get user / the user ID. And this endpoint returns JSON. So sometimes the endpoint returns the detail and the name, and the name and then the age. Sometimes there's no age. So you would say that this endpoint has two potential responses, which is very easy to learn. So if you as a human now, I tell you this, that this endpoint only returns this. And then in the next slide, I show you a response that has, I don't know, account number. You would say, was this intended? Is it a new feature? But you would catch it very quickly, right? As a human, you would just see the pattern and you catch it very quickly. So why can't we make machines, or why can't we analyze our data and get this understanding and do this with machines? So, sorry. Yeah. So it turns out it's very possible. So step one, you flatten the data. So all of those responses on the previous page, if we flatten it, we can get something like this. That we can get that we have two fields, detail.name, and we have some examples of what those fields are. And then we have an age, which is basically always a number. So it's very obvious that it's always a number. And this is an example of a function to flatten. We don't have to spend time here. I just wanted to show you some Go code. But it's basically a recursive function that keeps calling itself. And now what if we go a step further and then take each of these fields and hash them? So we take field number 1, we hash it. Field number 2, we hash it. So what does that mean? It means we have a representation of all the fields that is pretty short, pretty deterministic, pretty succinct. So this is XX hash, 32-bit XX hash, which means to always be 1, 2, 3, 4, 5, 6, 7, 8 characters. So even if I give it, if I have a very complex API that has detail.name, .this, .that, that is super long, it will end up being exactly this. So that means I can easily have a list of these hashes that represents each of these shapes, right? So remember, we had two shapes. We had a shape where, a situation where this endpoint will return both detail.name and age, and sometimes to return only detail.name without the age. So we can have a list of all these possibilities, and then we can even take this, all the hashes within one shape, and hash them again, and we get exactly this compact value. And this is a data structure. Maybe I can ask people. There's already a spoiler, but who wants to guess what data structure that is? Where you have a bunch of hashes, and then you now hash the hashes. And so you end up with one very short hash that represents all that data.
Merkle tree. It's sort of a binary tree structure.
You're correct. So yeah, it's basically a Merkle tree. I unfortunately put a spoiler in here. But yeah. So now we have this one hash that represents one of the shapes. And remember, we have another example where there is no age. So this is also a hash that represents this shape. So that means we can have two hashes in our database that represent this entire endpoint. And if tomorrow, so here's an example. So this small value here represents the first kind of response where there's an age, and the other one represents the second kind of response where there is no age. So if tomorrow now someone realizes, oh, what do we do if instead of a number, user is an alphabet, ABC, we want to return an error. So now we have a different kind of response, which is an error. So now we have three shapes, right? So we now have three shapes. So these three very short hashes represent this entire endpoint. And it's super easy to store this tree in a database or just keep it in memory because it's so small. And then you can compare all the requests that come into your server against these three things. So this is just a graph of what a Merkle tree is. So you have a bunch of data, you hash it. You can hash the hashes, and you still get a very short hash that basically represents all of the data below. This is very commonly used in blockchain, actually. So most blockchains are built on top of this. Why does this matter? So it matters because you have a lot of data. Usually, sometimes you have systems that are doing millions of requests per hour, per day. You don't want to, there's a very naive way that you can analyze this data to catch breaking changes. So you can say, go through the response, pick each field, maybe store each field in a database, and then every time you get a response, you check each field. Is this field in the database? Yes. If this field not in the database, oh, this is a new field, so it's a breaking change. But that's expensive. Imagine all the database calls you'll be doing for each item you're analyzing. So at scale, it's not practical. But by having these small hashes, you can even keep it in memory, do all this comparison, and not have to go to the database. So you can process millions of requests per minute even. Okay. And then you can even take it a step further and use a data structure called a Bloom filter. So I'll show you what a Bloom filter is. I think I have an image. So a Bloom filter is it's really a number. It's like an in64 number. But even though it's a number, if you represent that number in binary, you have this long 0, 1, or 0, 0, whatever of that number. But you have all of each of the zeros, each of this is the position, right? So you take a bunch of data, you hash it, use a hashing algorithm that returns an integer within that range, within the range of 0 and the maximum of in64. So for each data, you toggle one of these locations between 0 and 1, right? You just toggle. So, but just for the sake of this, I just stuck with the keys. Huh? Please go.
So how do you handle false positives in Bloom filters? Yeah.
That's a very good question. He asks, how do we handle false positives in a Bloom filter? So a Bloom filter is actually a probabilistic data structure, which means you actually expect false positives. So the whole point is that it's like an optimization. So before I do any of my expensive calculations, I check to see if it's positive in the Bloom filter. Then I now go and do my calculation. So it means sometimes I might do a calculation that I did not have to do, but then it's fine. Does that make sense? I'll give you an example. In pretty much all of our databases, like in Postgres implement, okay.
You know, in your case, you would have many keys that are probably going to be positive. So the exceptions are keys that are not there yet. Well, that is what I think you're trying to achieve. Like you have many keys in your JSON, for example, that are already stored in the Bloom filters. And then you want to know which keys are actually not there yet. So I think that you continue to hash the functions, and then most times what you get are keys that are there. Is Bloom filter really?
I think Bloom filters have false negatives actually, not false positives, right?
No, they can tell you that a key is there, but while it is not there.
Oh yeah, true, that's false positives.
Yeah.
So I think the main point, so knowing that a key is, so I think I have to think about this a bit. You know, on the spot I'm mixing them up. Yeah, but we can chat about it properly. But in any case, this is just an extra optimization that you can take, you know, just to speed things up. But even just reducing it into those list of hashes means that it's already very compact. And you can, for example, even without the Bloom filter, have a list in memory and just store that list. Because each of the items is basically maybe a 32 bits word or something. You end up with a list that is always going to be very small or fairly small. So I'm actually going to end here. The whole point of today's talk was just to encourage us, basically to treat requests as data. So if you record and store these requests, you open new possibilities. For example, more realistic load tests that we did. Or you can even go a step further and now use this to, for example, catch breaking changes, generate open API specifications based on this data that you now have. You now have a generalization of, what are all the fields in this real-time service, sometimes the legacy service, which we really don't know what's going on in there, but now you have enough information to, for example, generate a specification, etc. Yeah. So the other stretch goal is just excite you a little bit about topics like just data structures and algorithms for different things, because it's very common in our industry that we feel like data structures and algorithms are pretty useless. Basically, people say that all the time. Like, why do you spend time looking at some DSA book or, when you would never use it in your career? Unfortunately, in the real world, a lot of things, like when you need it, if you don't know about some of these things, you can't use them to solve your problem just because you don't know it exists, right? So you don't need it until you need it, and then you're kind of screwed.